Hello, how are you? I hope you're doing good. Welcome to today's lesson. Today we are going to look at how to determine the water loading in an overhead slab. And we are going to consider some three structures here. Where do you place your water tanks, what guides you, and how to determine the loading from the water to the slab. Considering the image shown here, this is a residential flat, and this presented is the roof terrace with hanging lines for clothes. And the roof terrace is an open terrace. We also have a roof, a slab for the staircase area, the staircase for this section. Then we have this roof for this room at this place. So if I'm going to place my water tanks on this roof, I need to consider the capacity of my water. Therefore, I have to get the total population from the units in this flat. And then I use the codes for design. I use the per capita consumption per day. And I can be able to determine the total volume of water I need in a day. This is what will guide me to determine the amount of water I will place on top of this structure. It is also expedient to have a tank at the underground section, which will act as a reservoir for the incoming water before it is pumped to the roof. Therefore, if I was to place water tanks here, I would consider designing the structure in a way I'm placing my water tanks at this level, on top of this floor, and on top of this staircase roof. This is because these are at a higher elevation than here, so I'm going to have enough head to create pressure for my water in all the units. Sometimes this water can become insufficient, and the developer might want to place another tank anywhere on this terrace. Is that right? If the slab or that section has not been designed for a water tank, then you are risking as a developer because that section is not sufficient to carry that water load. And sometimes we have seen, actually, I have seen a structure that has come down as a result of a developer placing water tanks at one area, along an area that had not been designed to handle that. And simply the building started tilting, and later on it came down. So we should really consider where we place our water tanks. Today's lesson is basically on how to determine the loading from the tank to the structure. That will be to the slab, and that loading is then later distributed from the slab to the beams and then the columns. So in this structure, I would consider placing my water tank here and here. And if these are insufficient, then I would select an area within this terrace to place my tanks, probably maybe here. Or I could design the entire terrace to handle water tanks. That will give the developer the leeway to place water tanks whichever place he pleases. But again, that makes the cost of construction expensive. So it is good to highlight a specific section where you would prefer your water tanks to be placed. Next, you can also this structure. You can see this is a flat roof, just like this one up there. And within this, the water tank has been placed at some section here. And it could be that the designer designed for the water tanks to be placed anywhere on this slab. So the developer can place the water tank anywhere. Or the slab at this section was designed to hold that water tank. Also in this, although it's not so clear, you can see it is a roof, and we have three water tanks placed, all of them in line here, and that means they are supported by actually this is one of our projects, and these tanks were supported by a reinforced concrete floor below them. Now, how do we determine loading from this tank to the slab, or from this tank to the column? Some people determine the total volume of the tank, and then they use the density of water and distribute that on the entire floor. Is that right? We are going to see that in a short while. Normally, the density of water is taken as 1,000 kilograms per meter cubic. Therefore, let us assume a 1 meter cubic water tank as shown here. This is a cube with 1 meter dimension in all the dimensions. Therefore, this is a 1 meter cubic water tank. Also, let us assume that 1 kg is normally 9.81 newtons, which is approximately 10 newtons. Therefore, since 1 kg is 10 newtons and the density of water is 1,000 kilograms per meter cubic, therefore the density of water is 10,000 newtons per meter cubic, which is also equal to 10 kilonewtons per meter cubic, as you can observe here. Since a cube of 1 meter cubic has a flow contact area of 1 by 1, that is 1 meter square. When you consider this cube, the contact area is the area here. That is this one multiplied by 1, which gives you a 1 meter square contact area. The load of the water is 10 kilonewtons per square meter. This one. Remember, the water tank was 1 meter cubic and this was 1. Therefore, because 1 meter cubic gives you 10, it's here. 1 meter cubic gives you 10 kilonewtons. Therefore, we have 10 kilonewtons acting on an area of 1 square meter. That is what we are saying here. Since a cube of 1 cubic meter has a flow contact area of this, and it has a density of this, then the load of the water is 10 kilonewtons per square meter. Perhaps let's consider tanks of different sizes. These two tanks have the same volume. When you consider this, it has a contact area of 1 but a height of 2. So that is 1 by 1 by 2. It gives you the volume of 2 meter cubic. That is the total volume of the water. When you consider the second tank, it is the same size, but the contact area is 1 by 2, which is 2 square meter, and the height is 1. Therefore, the volume is 2 cubic meter. Let us determine the load of water from the tanks. This tank has 2 cubic meter, and 1 cubic meter gives you 10 kilonewtons. Therefore, or rather, the density of water is 10 kilonewtons per cubic meter. Therefore, the total load of the water from this tank is 20 kilonewtons. When you consider the second tank, it is still 2 cubic meter, and the total, the density of water is 10 kilonewtons per meter cubic, which will still give you 20 kilonewtons. So the loading from this and this are equal. But what is the aerial loading where the tanks are resting? How much load are they exerting at that level? When you look at the first tank, you take the load, which was 20 kilonewtons, you divide by the area, the contact area. It was supposed to be 1 square meter, not 1 cubic meter. So 20 divided by 1, you get 20 kilonewtons of load at that point. It is just 20 kilonewtons. When you take the second, this is per square meter, not per cubic meter. So this first tank gives us 20 kilonewtons per square meter. Why? Because the contact area is 1 by 1. The second tank, you take the load and you divide by the contact area. The load is 20 kilonewtons. The contact area is 2 square meters. So 20 divided by 2 square meters, this is square meters. It's supposed to give you 10 kilonewtons per square meter, not meter cubic. So the second tank gives us 10 kilonewtons per square meter. The first tank gives us 20 kilonewtons per square meter. Remember, these are square meters. They are not supposed to be cubic meters. That was a mistake. Therefore, the first tank loads my contact area of 1 by 1 more than the second tank because of the more contact area. And remember, simply from physics, pressure is force over area. So that is what has been explained here. Let us consider a different shape of a tank. Let's change the shape of the tank to the circular one as shown here. The total volume of water from this tank, it's given by contact area. The contact area is pi r squared multiplied by the height, which is 3. Therefore, that is the volume, the total volume, which is pi r squared multiplied by h, which is pi r squared. H is 3, that is 3 pi r squared. The total load from our water is equals to volume times density. Our volume is 3 pi squared, pi r squared, 3 pi r squared. That is our volume. The density of water is 10 kilonewtons per meter cubic. So you multiply 3 by 10. Therefore, the total load from the water is 30 pi r squared kilonewtons. That is the total loading of our water. The total load from the water now per square meter is load divided by contact area. The contact area was pi r squared. So you take the total load, divide by the contact area, which is pi r squared. That gives you 30 kilonewtons per meter squared. Therefore, remember, when I look at this, the height of this tank was 2. The loading per square meter was 20 kilonewtons per square meter. We corrected this. The height of this was 1. The loading is 10 kilonewtons per square meter. The height of this was 1. The loading was 10. And this has a height of 3. The loading was 30. So what do you determine from that? Therefore, we can conclusively say that to get the total loading of water to be distributed to the slab, beams, and columns, we take the height of the tank, this height, we multiply by 10. That will give us the total loading of the water in kilonewtons per meter squared. So instead of carrying out all these tedious calculations, just determine the height of your tank, multiply that by 10. That should be your area per square meter. Therefore, there is a note here. Some designers take the total loading of the tank, assuming this tank was, where was the total loading? This is per square meter. So sometimes they calculate the total load, which is this one, 30 pi r squared kilonewtons. They determine the volume and they multiply by density to get the total load. Then they distribute the load to the entire slab area. Assuming that is such a tank and it is going to be placed here, they get the volume of the tank, they multiply by the density of water, and then they divide by the area of this slab. That is wrong, because what if I place that tank at this corner? That means I'm going to have more load at this corner and no load here. Or what if I place one tank here and then I place another here of the same capacity? It means I will have under-designed. Therefore, you just design the slab, the entire slab, to support such a tank placed at any location in that slab. Unless you have an exact location where you want to place your tank, that is when you can design for such an exact place. But to be safe, design your slab in a way that if the tank is placed here is safe, it is placed at the center is safe, if it's placed at the edge it's safe. That is why when you're designing the tank, do not calculate the total load and then you divide by the slab. No. Determine the height of the tank and then multiply by 10. That will give you the water load per square meter, and you will be good to go. This is wrong since the loading is only concentrated at the area of contact between the tank and the slab. That is what we have said. Like in this case, the loading is only at this point. So if we take the total load of the water and we we distribute it throughout the entire slab, we are going to mess because we will have under-designed that slab. So we just did the design for the contact area at where the tank is placed. Since in most cases one cannot control the exact location of placing of the tank, it is advisable for one to design the entire slab to support the tanks when placed at any location on the slab, just as I explained here. You design this entire section to handle your water tank when it's placed at any location. And I think we can also look at this question here. Is the water loading treated as a live or a permanent load? Remember, sometimes the tank is empty and sometimes the tank is full. Therefore, I am tempted to assume that the loading of my water is a live load. Is that the case? When you consider the British Standard 6399 Part 1, we are going to see how to consider that load. This is the code of practice for dead and imposed loads. And I'm going to read section dead loads. Dead loads are calculated from the unit weights given in that or from the actual known weights of the materials used. Where there is doubt as to the permanency of dead loads, such loads should be treated as imposed loads. When permanent partitions are indicated, the actual weights are included in the dead load. Now next is where our concern is. The weight of tanks and other receptacles. What is a receptacle? A receptacle is simply an object that is used to hold something. So a tank is just an example of a receptacle. A receptacle could be a silo that is supposed to hold cereals and such. So the weight of that tank and other receptacles, if they exist, and of their contents are considered as dead loads. So it is the tank and its content, both are considered as dead loads. These loads should be calculated for the cases when a tank or receptacle is full and when it is empty. So we should calculate this load as a permanent action, as a dead load, and we should calculate and include it in our load combinations when the tank is full and when the tank is empty. Why? When the tank is full, we will have our worst design case scenario, where the most onerous case, where this is the maximum load that we can have because the tank is full. But when it's empty, we use it when we are calling out the uplift check, when we are doing wind design. That is when we consider that the tank is empty so that the building can be light, to ensure that the structure is designed to be safe against uplift. Therefore, that is how you consider your water load. Summarily, I could say, when you have your tank, take the height of the tank, multiply by 10, and you will have your loading on that slab per square meter. So you take the entire section where you want to place the tank, and then you can design it for that load. And you should treat that load as a permanent action and not as a variable action, or rather as a dead load and not as a live load. Therefore, thank you very much. Today's lesson ends there. It was as simple as that. And many people confuse this. I hope this video has been helpful. Thank you. See you next time. Adios.